we may have resurrected the live stream on a different link to before, but I'm just trying to test it now. I mean, I'm still live streaming, I think. Yes. Okay, I think it's working. Yep, seems to be working. Okay, looks like people are joining back. Let's check I've got the speakers, or the people who can answer the questions, who are also speakers for the next sessions. We've got Paul. Yeah, great. And I think that David should be here soon. I just saw him in a breakout room, so. Okay, I'll just give it 1 minute to let everyone join. Okay, hi everyone. We'll begin our next session now on foundations. On foundations and programming concepts. Just to remind you that the proceedings for Padl are available here on the website. So they're online now. You can download those free for the moment. I think they stay free for a month. Some of the articles are open access, but not all of them. But you can get them open for next month. Right, so on to our first talk of the next session. We have Paul Tarot talking about a family of unification-oblivious program transformations and their applications. So that should...
Hi everyone, I'm Paul, and I will talk about a family of unification-oblivious program transformations and their applications.
Sorry, can people hear that?
I can't hear anything.
You can't hear it?
Nope.
No. Okay, let me try that again. I thought it didn't seem right. Okay.
Hi everyone, I'm Paul Tarot, and I will talk about a family of unification-oblivious program transformations and their applications. So the set of programs that those transformations apply to is a Horn-Clause program, so subset of Prolog, but a core subset of Prolog. And once you get that figured out and, let's say, implemented, everything else is relatively obvious, depending on how many Prolog systems you implemented in the past, at least. So our transformations that we will describe here are morphism between term algebras. They commute with unification and then consequently close unfoldings. And then consequently, Prolog's LD resolutions. They are composable and preserve the operational semantics of Horn-Clause programs, and they have a simpler execution algorithm, the resulting programs, and they can be compiled to a minimalist instruction set. So we sketch a Python 3 implementation, but we have ported more or less the same to Swift, Julia, and C. And we have the complete set of implementations at this GitHub site of mine, Logic Transformers. So some of the motivations why we are doing that, Prolog's core execution algorithms combine Horn-Clause unification and then backtracking, and this is all wrapped together as LD resolution. Once familiar with it, one is likely to find out that the underlying mechanism is really very, very simple. So we have two questions that we would like to answer here. Can we bring Horn-Clause logic to a form that's simple enough, as simple, let's say, as the lambda calculus in terms of S and K combinators, or even simpler, the X combinator? Can we derive from an actual implementation? And the approach that we will follow is that we will revisit Prolog's core execution algorithm and make it as self-contained as possible, while also formally uniform. And then we discover some theoretically interesting and at the same time easily implementable reductions to unusually simple canonical forms. So let's look at a term algebra. So it's made of a set of constant symbols, a set of variable symbols, and a set of terms. So what we have for them is that the constants are in the algebra, the variables are in the algebra, and then the trees that you can build by putting one of the constant symbols in front here and subtrees here, also in the term algebra. And in particular, if you want to just stick to binary terms, which means basically function symbols of arity 2 in Prolog terminology, then you would have that all constants are in the algebra and all variables are in the algebra. And then with this little constructor here that looks strangely enough as if it were the arrow in type declaration, which we will mimic happily here. We will have a transformation that turns something that looks like this into a binary tree representation among the transformations that we will cover. So the next step would be to bring in the unfolding operation that's instrumental in Prolog's execution mechanism. So let's denote U of T1 and T2, the result of applying the most general unifier to them, and then it doesn't matter to which of them you would apply this substitution. If the MGU exists, then those two are the same. But if unification fails, which could happen, of course, that's how Prolog selection mechanism works, then we assume that we have this bottom symbol here, and then to propagate failure, you would say that the unification of T and the bottom failure, the bottom symbol that indicates failure, would be still the bottom symbol in any order. So with that, you basically have here, together with the associativity property of unification, again, unification after it got applied, and the little details like, let's say, standardizing all variable names. With that, you have this associativity property of the unification operation. So this brings us to the monoid of Horn-Close unfoldings and to LD resolution, which is Prolog's SLD resolution, but spatialized to the first atom in the body of a clause, and of course, Deff's first iteration when it turns into the actual execution mechanism of Prolog. So the essence of that is that if you have a clause that looks like this and one that looks like that, you basically would look at the first atom in the body of this one here, and then you would unify it with B0. You will apply that unification operation to everything here. That's why the primes, the unification has been applied. And then you would get the next step in the unfolding process, basically. And we denote with this symbol here the operation. And we also assume, of course, that failure propagates here with the same semantics. Bottom operated with X is X operated with bottom, and then all that is bottom. So now we can look at Horn clauses forming a monoid with the unfolding operation. The unfolding operation is associative, and the clause, here we are very liberal. We said that a variable can be a term on its own, and any combination of terms here is actually a Horn clause. So then if V is a variable, it's easy to see that this actually works as the identity element. So the monoid structure associated to a term algebra T can also be seen as a category, of course, with a single object in which its unfolding operations act as morphisms. That's another view of the same thing. The monoid of the binary clause unfoldings is just a specialization of the previous one. Looks a little bit simpler here. We have A1 here canceling with B0 after unification and giving A0 and B prime, of course, and B1 prime, where the prime indicates that the unification operation, the MGU, has been applied. And then again, failure propagation via this rule here. So they form a monoid, same structure, and the next transformation now would be binarization. I used that in building a Prolog system a long time ago called BinProlog. Someone might still remember it. Still runs, in fact, pretty fast. So it's, that was more an abstract machine specialized to executing binary clauses. But let's formalize here in very simple terms the binarization transformation. So if you have the Horn clauses on algebra T and then the binary clauses on the same algebra, then the binarization operation would work like this. It's kind of adding continuations on the left and on the right and propagates them. So in the case that we have a term here, f of A1 to AM, and then this operation with B that actually takes B and places it as the last argument of the predicate term, in this case F. But we do not distinguish between predicate terms and so things in the Herbrand base versus the Herbrand algebra. We all happily conflate them because Prolog does that, and formally everything here is as clean as it would be in a slightly more traditional way, as usually expressed in logic programming textbooks. So what we get here is that LD resolution is now oblivious to binarization, which also means that we have this relation here that if you apply the binarization to C1, and then you apply it also to C2, where C1 and C2 are two clauses, and then you do the unfolding there, that's exactly the same thing as if you did unfolding before binarization, and then you binarized. And from this, you actually infer that the binarization operation is injective, and it has a left inverse here. So if you apply the binarization in reverse, you unbinarize, right? And then you unfold the binary forms of those two, you would come back and you get the same thing as if it were the original unfolding of the two clauses, which also means that you could apply this transformation, do the implementation of a prolog system, which I did with Bin-Prolog in the past, and then come back and make things look as if nothing happened, as if you just did an unfolding step between C1 and C2. So a new bijection here, this one is actually a new one. It's not very well known that you can do it to arbitrary trees, in fact, but here it is. If we have a constant, then the binary tree transformation BT from T to the binary trees here would just keep that constant untouched. If it's a variable, it keeps the variable untouched. And then if you have a term which is of this form here with multiple arguments, then applying it to X would transform in this chained recursive transformation, of course, of all the BTs applied to all the arguments, and then F being in the last position here. And this is a bijection, actually very easy to show for arbitrary trees. This is the constructor, and we assume right associativity here, so this reads a bit better. This is an example. If you apply it to F of A, G of A and B, and then B again, then you get A, this implication symbol, A to B to G, then following the structure here with G at the end, and then B again, this B here, and then finally F, the F here. And it's reversible, this small prolog code that does it at the site that I mentioned initially. So now something that's well known, it's an equational form of the binary term algebra. If C is a constant, then the equation, think about it as unification between X and C is just X and X equal to C, so untouched here. Same for a unification between the term and the variable, it's just that. And then if here we have a binary term, so that's the constructor, those are the two arguments, then the equation XA is the nested conjunction of X equals to this arrow term here with new variables X1 and X2, right? And then an equation that equates X1 with the original X1 here, and X2 with the original X2 here. It doesn't need to be done for binaries, it's just a bit shorter for presentation purposes. It works, of course, for arbitrary terms, NRE terms as well. So with that in mind, now if we extend it to a binary, in this case Horn clause, then you would have the equational form of the A0, A1 here. So that's a binary clause, head and body. That would be a new predicate symbol, P, that shouldn't occur in the program, applied to a variable here, X0, a new variable. And then here you have the equational form equating X0 to A0, and then the rest of the body. And then finally the same predicate, new predicate symbol, unique predicate symbol that can be shared between all the clauses in the program that would be applied to X1. So with that, actually, we have a little theorem here saying that LD resolution on this program on a program P computes the same answers as LD resolution on the equational form of P. Moreover, the same applies when permuting the order of the unification of equations in any of the clauses. So we have suddenly a lot of freedom in how we arrange our code. And in fact, from here, we will get to the idea that a way to compile Prolog, or the Horn clause subset of Prolog at least, would be to compose some of those transformations. And what we have here is clearly the fact that if we have those two transformations that are that have left inverses, then we can apply the same thing to the composition of them. And we have here a way to actually combine the transformations and get the same thing exactly as if just one of them were applied, the same reduction formula here. So the composition of our transformations enables compiling Horn clause programs to alternative forms, which when executed will compute the same answers. So now, this is one of my favorite DALI pictures. Step by step, from something complicated, we will reduce things until we get to something like this. Maybe more could be done here, but that's good enough. And we will apply this to turn our theory so far into a practical implementation technique. So let's see what happens then if we do that. We get a very nice canonical form that consists of, we call it a triplet normal form, that has a single unary tail recursive predicate with data log clauses. This is that new predicate symbol P that got introduced, a single predicate function symbol, and a single non-data log fact. So everything is data log now except one single fact of verity 3, referring to the function symbol, to the new function symbol here. And that new function symbol is that arrow operation that we introduced. We'll see on some concrete examples how that actually looks. But the idea is that we just apply the combination of binarization, then turning every term in it into a binary tree, and then into an equational form. So we apply them into left to right order in this case. The unification operation can be encapsulated as the predicate unify 3 in this unit clause here, which actually, when called as U of A, B, C, is equivalent to the unification operation AROB equals to C. That's very easy to see here. And in fact, the Prolog implementation of that looks just like I mentioned it. We have the predicate P1 with its self-recursive last call. So P here, P there. And those are the unification operations with some variables and constants, and that's all. So this looks like a data log program, but of course, the critical thing here is that U is not a data log fact. But from here, we are ready to derive now our three instruction assembler. The D instruction that says, well, define A here, and then the proceed instruction here saying one step further, as we have seen with those elephants, smaller and smaller steps until we finish. And then we have the unification operations here. So that's our simplified canonical form for Horn clause logic. Now we could start playing with implementing that, and here's a sketch of a virtual machine. We have implementation again in Python, Swift, Julia, and C. The first one in Python took about 2 days, and then 1-2 good afternoons for each of these. Spent a bit of time in C, though, to kind of optimize it. You will see a little bit of execution benchmarks for it. And this is again at this site, all put together in one big folder. So a runtime instruction interpreter consists of the following. We have an inner loop, and we have a trampoline mechanism that avoids recursion and enables a last call optimization. So I wanted to turn this into a proper, fully, correctly implemented, horn clause logic system. And that means that we handle memory management as well. We borrow garbage collection from the implementation languages, and those three are all very lucky to have it. Or when we are in C, plain C, there is this very nice conservative BOEM garbage collection extension to C. It's just a library that you can add. And with that, you get then a prolog system that can recurse forever, and provided it doesn't create too many terms. And then you have a horn clause prolog virtual machine that's extensible eventually, which we didn't do, but that's a few hundred lines of code. So that's relatively quick to build when that's needed to be quick. The inner loop here, very quickly, we're executing the U operation, the proceed operation here, and the define operation, relatively compact, and we send back to the trampoline what we want to do next. And that brings us actually to the outer loop, which I will mention in a minute, but let me just summarize very quickly the D instruction marking the entry to a new clause. The U instruction does the unification, and this one marks the end of the unification. And then the trampoline here just makes sure with a stack that there is no recursion there. So those are the performances here, not very bad. We actually get to about 10 times slower than SWI Prolog, but if you just use the emulation in Prolog of our instructions, then we're actually faster with this. And my conclusions to that are that if we have composable unification-oblivious horn clause program transformation, then they can be useful for succinctly understanding and implementing Prolog's core execution algorithm. And the three-instruction assembler can help porting unification-based programming inference mechanisms to platforms where resource limitations or urgency of implementation matters. IoT devices, small drones, CubeSats, small appliances, wearable devices, portable or implanted medical devices. And the final conjecture here, basically, if a term transformation that has a left inverse and maps variables into variables and constants into constants, then it is oblivious to unification and can be extended into an unfolding monoid on horn clauses that commutes with LD resolution. Thank you.
Great, thank you very much. So over to questions. I will kick things off while everyone else says, oh, sorry, hang on a second. Sorry, I'm getting some problems on my side. Hang on a second. Okay, sorry about that. I was about to ask a question, which was, okay, so you have this really neat way of like completely decomposing how basically the guts of Prolog works. And one thing I wondered is, could you then retarget this at something like Datalog, which is you've got a sort of a subset of Prolog, and use that to sort of understand some of the fundamental differences in how you implement Datalog compared with Prolog, by looking at these little sort of nuts and bolts?
Yeah, that's an interesting question. Now, the thing with data log is that it stops being data log if you apply any of those transformations, because when you introduce, let's say an equational form on a ground term, the term is not ground anymore because you introduce new variables. So that's one of the things. Otherwise, if you look at data logs, let's say bottom-up execution mechanisms, for instance, that's something that it's not very usual to do when you have unification at hand. Usually are goal-driven. There are too many possibilities there, in a logic program, and you do not want, in the general case, to start with a bottom-up execution mechanism. I know that Gopal Gupta is doing that for ASP, actually, to make it a goal-driven execution mechanism. So the impact on the data log, of course, it would execute a data log program because that's just an instance, a subset of a Horn-Clause program. But other than that, I wouldn't see that it simplifies it in a radical way, because one of the steps here is to turn something into data log, except for the one critical unification clause. Now, it could be very interesting to see if that could be turned into an execution mechanism for something that's like Horn-Clause, let's say an ASP program in which you would implement the location of all those objects as logic variables. That would be interesting to mimic in ASP a unification-based execution mechanism. But here the scope was really to just focus on Horn-Clause, full Horn-Clause program that can be turned into a free instruction assembler, as simple as possible, but not simpler.
Great, thank you. Since we started slightly late due to technical difficulty, I'll take one more question. I think, Michelle, can you, you've got your hand raised. Go ahead. We can't hear you though. Still can't hear you. Just can't hear you. I can see that you're trying to talk. Oh. Okay, I think he's just reconfiguring.
Yeah, do you hear me now?
Great. Yeah.
Yes, we can.
Awesome. So my question would be whether we can apply this technique when we want to process the multiple instances of the same predicate in array-like fashion. Instead of doing it one by one with backtracking, we would like to process like 100 queries or 1,000 queries.
You have a bit of extra freedom here, let's say by executing the unification operations in arbitrary order. That was one of the reasons why I was playing with this, because you would like to run a Prolog system on a GPU eventually. And the parallelization issues for this are very similar to the parallelization issues with Prolog in general. Prolog unification is under the hood destructive assignment. So it's not as simple as in a functional programming language to run things in parallel unless you really, really engineer those constraints about what needs to happen first and memory access mechanism. But other than that, I guess there are some freedoms here to run the unification operations in parallel, because it can be a very long stream after you, let's say, do repeated unfoldings, and then you have hundreds of unification operations working at independent memory addresses eventually that can be all performed in parallel.
Great. Okay. Yeah, that's interesting. Great. Thank you very much, Paul. Let's give you a round of applause again.
Thank you.
And we'll now move to the next talk. I'll try and do it right this time, which is given by David Young on adding pattern matching to the Haskell-based deeply embedded domain-specific languages. So it's David Young with his colleagues Mark Grebe and Andy Gill.
In this talk, I will discuss adding pattern matching support to embedded domain-specific languages in Haskell. Embedded domain-specific languages, or EDSLs, form a powerful approach to solving problems within particular problem domains. However, it is often challenging to capture certain control constructs in EDSLs, as these control constructs are frequently not reified by the host language. An example of this being case expressions in Haskell. In this talk, we will present a technique for capturing pattern matching in a Haskell-hosted EDSL, and we will have a corresponding representation for algebraic data types, or ADTs. The fact that we are able to capture pattern matching by uniformly acting on ADTs using this representation is really the key idea of this work. This representation will support sum types, product types, as well as recursive types. We will also need to add lambda expressions to the deeply embedded EDSL in order to fully support the machinery behind the scenes necessary for capturing pattern matching using this particular method. We will also implement tail recursion in order to take full advantage of recursive types. So as I said, EDSLs are powerful tools. Applications include targeting accelerators such as FPGAs or GPUs, as well as 3D graphics description languages such as are used in virtual reality. And EDSLs can often use host language features, and in Haskell, a prominent example of this is usage of the type system, which is particularly, well, it's a static type system and it is a strong type system, so it allows many invariants that we care about preserving to be expressed within the type system, which is then checked at compile time. However, pattern matching is desirable to have in many EDSLs, but it is difficult to actually bring to use within an EDSL in Haskell. And this is largely because it is in part a control flow mechanism, and it is built into the Haskell language itself, and it is not exposed in a way that can actually be manipulated easily. So there's no direct way to capture it without accessing the abstract syntax tree, and we cannot really directly access the abstract syntax tree through normal techniques. Template Haskell is a possibility, but that brings its own challenges. And in order to address this, we will create a reusable representation for pattern matching using a GHC core plugin, and this GHC core plugin will access the abstract syntax tree of the EDSL code. This representation allows normal Haskell code to look at pattern matches that are given within the EDSL. So looking at the Haskell code in this slide, we see the example has a pattern match on X, which is an either of char and int. And we see that it is as a whole, example has type E of int. And E is the expression type for our EDSL language. So externalize brings a value from the host language, in this case Haskell, into the EDSL language. And this value, in this case, depends on this pattern match on X. And we want to actually capture this pattern match so that we can actually examine the pattern match within the EDSL and look at the structure of the pattern match and potentially translate it to something else. So, as I said, internalize brings a Haskell expression into the EDSL, and internalize goes the other direction. And we can see that externalize has this type, as shown in the slide, where there is maybe some constraint, and then it has type A to E of A. But how can externalize work? Well, externalize cannot be implemented as a Haskell function due to the issues I mentioned earlier. It has to operate on an abstract syntax tree. So the actual implementation is given by the core plugin. And it's also worth mentioning that a call to externalize so to speak. It's not an actual function, but a call to externalize, captures the surrounding function definition so that the function arguments can be handled properly, and this is necessary for the tail recursion transformation, which will be described in more detail a little bit later. Now, before we get to the implementation of externalize, we need to think about the expression type E and how might we be able to structure this type so that we can properly represent pattern matching. And before we even get to that, we need to think about how can we represent algebraic data types in a uniform manner. An important observation to make is that algebraic data types are constructed out of other algebraic data types in two main ways, as sum types and as product types. And overall, an algebraic data type is a sum of products. So considering this fact, we can abstract away details of any particular ADT, or algebraic data type, which would be the constructor names in particular. And these sum of product structures can be examined directly without these names kind of being present. And this representation where the names are abstracted away and it's a uniform representation of the actual sum of product structure is what we call the canonical type for the ADT. And now that we're able to do this, we only really need to think of things in terms of these canonical types. The type family E-repti gives the canonical type of a given type. And the instances for E-repti can be automatically derived for any type that is an instance of generic. Now, to give an example, consider this complex pair type which has two complex doubles as its fields. If we apply the E-repti type family to it, we see that we get a pair of complex double and complex double. Now, it is worth noting that we did not actually deconstruct this fully. Complex double is itself a pair of doubles, and we didn't fully go down into this structure when we, in the result of E-repti. E-repti did not fully descend into the structure. And this is actually a key feature that is important for implementing recursive types, as we will discuss later on. So canonical types, as I said, will turn any sum type into an either and any product type into a pair. And really the key idea of the whole thing here is that by operating on canonical types, so when we talk about representing pattern matching a little bit later, we only have to talk about doing it on these canonical types, and we don't have to worry about the specifics of certain ADTs. We can just convert it to its canonical type representation and work on that canonical type, which is something that we can do without knowledge of specific things, specific information about certain ADTs, such as constructor names and so on. So E-repti is a type family that's associated to a type class, and that type class represents all the types that can be used within the EDSL, and this type class is E-rep. Now that we have these two constructs, E-rep and E-repti, we can start to define the data constructors of the E-type. Now for the moment, we're going to set the first one aside. This is the construct rep, and we will note that the remaining constructors are all pretty standard data constructors for introducing ithers and pairs, that is sum types and product types, into a embedded domain-specific language. We have a data constructor that brings in left values of the left type of a sum type and of the right type of a sum type, and we also have a data constructor that takes in two EDSL expression language types and gives you back a pair within the expression language. Now that constructor at the very top, construct rep, it is used as part of the transformation from the host language into the EDSL. And it transforms a value that is in its canonical type to a more specific type. So using the example from earlier of complex pair, the canonical type was a pair of doubles, or a pair of complex doubles, and the original type was complex pair. So constructor up takes a E of that canonical type, and it gives you back a E of complex pair. And this is how complex pairs, for example, are introduced into the EDSL. So now we can turn our attention to representing pattern matching, now that we've looked at how ADTs are represented. So a pattern match is represented using this case exp data constructor in the E type. And there's a constraint in this type, but we will ignore that. It's not too relevant for this talk. And we will see that there are two fields. The first field is the scrutiny of the match, which is the thing that is being matched on. In Haskell, it would be the thing between case and of. And the second field is something that represents the list of match alternatives. And this uses a sum match type, which will be discussed in more detail shortly. So the sum match type represents essentially a function, well, E of sum match rep tie T and R, as shown in the slide, represents a function in the EDSL from E rep tie of T to R. It is essentially a function which matches on the possible alternatives of that sum type. And more specifically, it is a list of E prod match values, one for each possible alternative in the sum type. So within each branch of the sum type, we're matching on the product. Since remember, ADTs are sums of products, we have a list of matches on a match on the sums, which is expressed as a list of matches on products. And we can see here that the data constructor is corresponding to the introduction of this sum match, which I've highlighted, is corresponds to something kind of like const for a list. There's the case for the empty list where there's no alternatives or no remaining alternatives in the pattern match. And there is a special case for when there is only a single alternative. And we can see that in sum match expression, the first one that's kind of like const, it kind of destructures an either into something that matches on a product in the left of the either and another sum match on the rest of the either. So now we look at product matches. So product matches can also be thought of somewhat as a list. They're a little bit less like a list than sum match, but they're very much like a function. And in fact, they have a EDSL function. Generally speaking, they have an EDSL function inside of them. And this conceptually operates on one of the elements of a pair, and then it gives you back a function which deals with the second element of the pair. And this could be a nested pair of pairs, and so forth. And so that function gives back another prod match, and we can see that in this first constructor here. And again, we have a special case for when there is a single match, and when there are no more elements of a pair to match on. So as I said, in effect, it is somewhat like a function. E of prod match S of T and T is somewhat like a function from S to T. And in fact, internally, it is represented as a function. And when it's being translated into its reference semantics, and likewise for sum match. And we can see that currying kind of is represented at the very bottom of the slide, except that the expression types kind of are interleaved there. So as we saw, we needed a function inside the expression language, so we need some kind of representation of lambda or something like that of lambdas. And the way that this is done is using globally unique names, the Behrend-Rett convention. And it is also worth mentioning that when things like pattern matching and tail recursion are captured, when control flow is captured already in a deeply embedded domain-specific language, it is quite a bit easier to also capture lambdas, because then when you're doing something like passing in, like if you apply the lambda to a var with a fresh name, it doesn't encounter any control flow that will disrupt the var from being pushed all the way through the lambda. And typed names are also used internally, and those are just a wrapper around ints. So summatch and prodmatch are primarily type tags that are used in the GADT representing the expression language, but also, as I alluded to earlier, the reference semantics uses the fact that they wrap functions. So returning to our original example, we see that example gets translated by the core plugin into example prime, and we can see all of the constructor, or many of the constructors that we've talked about in action, so to speak, and I've highlighted the right-hand side of each branch in the generated deeply embedded case match. And here we see more details of the actual plugin transformation. There's quite a bit more involved, which you can see in the paper, but many of the most pertinent rewrite rules are given here. We can see that the rewrite rule for case expressions will introduce this case exp, and we can see that the list of branches, this B rule gets recursively applied to those and introduces some match expressions, and then P for product matches, which introduces these lambdas, which this A introduces lambda, and M marks a sub-expression for further transformation, and that's outside the scope of the talk, but you can see it in the paper. And as I mentioned before, there is something that recovers the reference semantics, and this is done by abs, which is more or less has type E of T to T. And this function uses helper functions, prominently summatch abs and prodmatch abs, which respectively give the reference semantics for matching on some types and on product types. And here we can quickly see that the action of prodmatch abs on prodmatch values utilizes the fact that prodmatch values are actually function wrappers, or wrap functions, and we can see how this is used in this excerpt from the implementation here for the reference semantics. As I mentioned earlier, erepti does not descend fully into types. It only goes into the first layer of types, and this allows recursive types to be implemented in a relatively straightforward manner. Consider the int list type as given in the slide. If we were to think about erepti applied to int list, if erepti descended fully into the type it was given and completely destructured it, then that would be a non-terminating type level computation, because it would never stop going into the recursive, the recursion of it. And it only actually goes into the first layer. So the type equality shown near the bottom of the slide holds, which shows erepti of int list is the same as either of unit and a pair int and int list. And we're able to do this due to the fact that whenever a pattern match occurs inside core, it only matches on sort of the first layer of structure. So each pattern match, we only need to deconstruct the first layer. We only need to destructure that first layer. So we can kind of do this as we go along instead of all at once. Here's a simple example of this int list in action and the externalize and internalize functions being applied to it. And the core plugin will turn this into an appropriate inappropriately translated case expression, even though it is on this recursive type int list. This terminates correctly and exhibits the behavior that you would expect it to. Notice also that this is an example of why externalize and internalize need to capture the function surrounding it, the function definition surrounding it, so that the arguments are handled properly. In this case, t is a free variable within the externalize, the argument to externalize, so this needs to be handled properly, and this is discussed in more detail in the paper. Now, tail recursion is useful for many reasons, but once you have recursive types, it is often useful to have some form of recursion, such as tail recursion, in order to make better use of them. And we encode tail recursion in this particular way shown in the slide, where we eliminate the actual recursion and turn it into a function that can be stepped over and over, and the equivalence to tail recursion is one direction of it is witnessed by the code given at the end of the slide. And this allows us to have this deep embedding of tail recursion as shown in the slide, where we have step and done, and then this sort of tail rec embedding that actually holds the function that represents a tail recursive function. And we see at the bottom of the slide an example of a tail recursive function operating on an int list. To conclude, pattern matching can be represented in a reusable fashion in a Haskell-based embedded domain-specific language. Note that we did not use any specific details of a particular problem domain. And this representation can be captured using a GHC core plugin. Now, this was made possible by a uniform representation of ADTs, that is their canonical type, and this canonical type establishes a scaffolding or infrastructure on which to build a pattern matching representation such as described in this talk and in the paper. Now, also it was noted that lambdas become easier to capture once control flow constructs, including pattern matching as well as tail recursion, are already captured, as you can do that technique of sort of pushing that var constructor through the lambda without it hitting a control flow, a conditional, essentially, such as a pattern match or something along those lines. Future work includes looking at more applications for this system and more examples of this in action, as well as a more in-depth comparison to template Haskell-based approaches for expanding the expressibility of embedded domain-specific languages in Haskell, and sort of a more in-depth contrast and a examination of the pros and cons of each approach. Thank you for your time.
Great. Thank you very much. I'll do a round of applause. I'll move to questions. I have a perhaps slightly technical question, which I'll ask to start off while everyone else is thinking. So I was thinking about the recursive types setup, and I was just trying to work out when you actually want to construct one of these. Let's say you want to construct a value of a list using the list example. I would have thought you still want to get the E constructor pushed down so that you can say you want to take an E of an A and an E of a list of an A, and this gives you an E of a list of an A. Doesn't that mean you have to push the representation down another level at that point? Or is that already happening?
Let's see if I'm understanding the question correctly. Essentially, that is not necessary due to that construct rep data constructor, which will take in a like disassembled or the canonical type for a type, and it will give you back something that that is that original type. So in the talk, there is that example where construct rep can take on the type E of pair of complex double and complex double, and it gives you back an E of complex pair. Mm-hmm. So essentially that constructor is why that's not really a problem in the constructing part, if that makes sense.
So for constructing the cons of the list, you would take an EA and an E. No, you would take an E pair of A, list A.
Yes.
Okay. Right.
And then
okay.
for the sort of second part of the const, you would have the actual value would have a construct rep.
Yeah. Okay, great. Thank you so much for clarifying.
Sure.
Okay. Other people's questions? Just unmute yourself, or you can raise your hand. Okay. There's a question from the Clouder, and I'm not quite sure who said it. So if there's someone here who just put that in.
I can just read my question or say my question.
Go for it.
So great work. I think this is really cool. One thing I'm curious about is if you've applied this technique to any existing Haskell EDSLs, or if you have any concrete examples of the kinds of programs that are now easier to do with this approach versus how this sort of thing was typically done in Haskell EDSLs before.
So that's a really good question. We have not gotten examples like that yet, but that's kind of the next thing that we want to work on. The running examples we've been using, there's some simple ones like I mentioned in the talk. Probably the most complex one is a Mandelbrot set example. And it's also worth mentioning that there is a C backend right now. So it does like fully go through all the way compiling to C the examples that do exist. But the most complex one is just a Mandelbrot generator. And in the near future, we want to look at exactly that, looking at more involved examples and looking at more specific EDSLs that we can apply the technique to. So thank you for the question. That's very good.
Because there are certainly applications in like GPU generation, code generation, where working with things like tuples and arrays is really awkward right now. So being able to match on a complex number in an array would be really convenient.
That's actually one of the very specific things we want to look at is GPU stuff. So.
Cool. Any other questions?
Hey, hi.
Go ahead, Lionel.
I think I didn't understand how you distinguish between constructors with the same arity, but which are distinct constructors. Because you said the names don't matter, but you must have a way of distinguishing two constructors of the same arity, right?
So it gets distinguished. Let's see. Let's see. So it gets distinguished because it eventually gets transformed into a like structure made up of eithers that are nested. And so you have the left and the right in the either, and those are distinguished constructors within the either. So we're kind of inheriting the distinguishability from either, if that makes sense.
Based on the order in which it's defined, I guess, in the data type definition.
I'm not entirely sure what you mean.
So you turn the data type into a bunch of ithers.
Ithers and pairs.
Based on the order in which the cases are defined in the data type definition.
Yes.
Yeah, okay. Mm-hmm.
Yep, so that's how it's distinguished. And that's also like how the correspondence works, is it's based on what order they are in the original definition.
Sure, yeah, makes sense. Thanks.
Great. Well, I suppose we better call it a day there since we're out of time. So another round of applause for David. Fantastic talk. And we can catch him and his co-authors later for more questions. I know I will. So thanks very much, everyone. That's it for Padl today. I will be back again in the morning. Well, no, not in the morning. Well, it depends where you are, right? Back again for wherever you are. It will be at 2:30 Central European time. And we'll be starting the day with our second keynote by Julia Liela on SMT-based constraint answer set solver EZ SMT. is very exciting. So more SMT related things. Jose, did you want to say anything else about tomorrow?
No, I don't think there is anything special.
No, I don't think
Just see you tomorrow.
Yeah, just see you tomorrow. Yeah. So thanks everyone, and yeah, do go and socialize on the Cloud platform. Try and catch some of the speakers if you didn't get to talk to them, and yeah, we'll see you all then. Cheers.
Bye bye.
Bye.